Okay, so we didn't have much time to work on this in class. I hope everyone goes through and watches all of this video. Some quick recaps here. Momentum is going to be conserved in a system. So that means like the total momentum. So if you have like two carts crashing, obviously like the different momentums of the different carts can change, but the total momentum has to be the same both before and after, unless there is an external force acting on it. So them crashing, there are forces, but those are internal forces to the two carts. External force would be like if they're also falling down, right? Then there would be gravity or friction, etc. But most of the time, it's going to be no external forces, so total momentum should be conserved. Elastic collision, kinetic energy is conserved. Inelastic, not conserved. Perfectly inelastic is a special case of inelastic where they stick together, and because it is inelastic, obviously kinetic energy is not conserved. In fact, this is the case where it's conserved the least. It loses the most kinetic energy. If kinetic energy is not conserved, that means it's losing kinetic energy. It's going into other types of energy. So whether it's going into probably not potential, more like internal energy, deformation of the object, sound, etc., heat maybe. But momentum will always be conserved in these collisions, again, unless there's an external force. Special case of elastic collision, if you have two equal masses, so like say you have a mass of 2 coming in at 3 and a mass of 2 coming in at -5, when these two hit, if it is a perfectly elastic collision, then they literally just switch velocities. So this will go at 3 and this one will go at -5 now. Or if this one's at rest, hitting something at rest, if it's 5 and M, now this one stops and this one goes off at 5 because they literally just switch velocities. In a collision, so in this case, when these two collided, the change in momentum had to be the exact same for both of them. However much momentum this one loses is how much this one gains. The impulse has to be the exact same, just opposite signs, because impulse is the same thing as change in momentum. Their forces, equal but opposite forces, Newton's third law, so it has to be the same force because it's the force on one another. But they will have different accelerations and different change in velocities. Think about your acceleration is F over mass. So if they have the same force but they have different masses, then they have to have different accelerations. Another reason impulse is the same is because impulse is technically F delta T. If you have the same force, and it has to be for the same amount of time, because there's no way this cart hits this cart for 3 seconds, but this one hits back for only 1. So if these two are both the same, then the impulse has to be the same. Impulse, same thing as change in momentum, completely interchangeable, means the exact same thing. Technically, impulse is F delta T, whereas change in momentum is M delta V, but they're equal to each other. If it is a constant force, then to find the impulse / finding the change in momentum is just F times change in time. But if it's a changing force, which is a lot of the time, so like something like this, force versus time, you can't just say like force times time because it's a different force. It's changing force in all of this. So we would do area under the curve, which is the same as multiplying this axis times this axis. So it still gets me the same thing, but that's for if it's a changing force, you just do area under the force versus time curve. And that would give me the impulse / the change in momentum. That's what this is equal to. In a collision, center of mass will remain at a constant velocity. So whatever the velocity of the center of mass was before, that will be the velocity of the center of mass after, unless there's an external force. Quick vocab, if you see the word inertia, just replace that in your mind with mass. And then careful with science, direction absolutely matters, and it's really frustrating to miss a really easy question just because you forgot to put a negative for it going left. Alright, our equations. These two are our given equations, P equals mv, and change in momentum equals F change in time. But you should also know, and you basically take this equation, the momentum is mass times change in velocity, so the change in momentum is just mass times change in velocity. And why it's not delta mv is because your mass isn't changing, it's velocity that's changing, which causes the momentum to change. Alright, number 1, we've got a 2 kilogram blob of putty moving to the right at 5, and it collides and sticks with another block that's moving leftward. This is a collision. Draw your before and your after picture. This one is going leftward, so put a negative sign, otherwise you get it completely off. And then it says that they stick together, so I'm going to assume it goes this way. It doesn't matter because I'm going to find out in a second. And now I want to find kinetic energy after. Well, in order to find kinetic energy after, I need to know their velocity after. So I'm going to use momentum plus, and make sure you put a negative sign there, 2v plus 0.25v. Now these two, I'm putting v for both of them, not like v1 and v2, because they are stuck together. They do have the same velocity. On this side you get 7.5, so you get your final velocity is 3.33. And then I want to know the kinetic energy after. So kinetic energy, you can think about it as just one object of mass 2.25 moving at 3.33 meters per second. Or you can do like 1/2 mass of 2. Think about it as separate objects with their individual masses going the same velocity. It doesn't matter, it's the exact same thing. You plug it in and you get 12.5. And if you didn't keep your calculator, you get 12 point something close to that, so you know it's 12.5. Number 2, I've got a graph showing me force as a function of time. So I've got an FT graph. I have the mass of a ping pong ball, and I have that it was initially moving to the right at 8, or sorry, to the left at 8, so that should be a -8. And that was the initial velocity, and I'm looking for the velocity after, so I'm looking for like my final velocity. So first let's look at our graph, because obviously we're going to need to use the graph. So what's happening is that there's some force applied, meaning that the momentum is going to be changing. I'm going to be gaining momentum in all of this because I have positive areas under the curve. So first things first, find area under the curve. This is a triangle, so base times height over 2. And my height is 6, and my base, most of you are going to say 3. Well, careful, because this is not measured in seconds, it's measured in milliseconds. So if you go to your, let me grab it. If you go to your equation sheet, it tells you what milli is. You don't need to memorize like the different prefixes. So milli is times 10 to the third. Where is it? Times 10 to the third. So I'm just going to say this is 3 times 10 to the -3, -3, not to the third, divided by 2. Now you put that in your calculator, and that's going to give me that my area, or my change in momentum, is, I think it's 0.009. Let's check. Let's see if, hopefully you can see that. So 3 times 10 to the, oh dear, 10 to the -3 times height of 6 divided by 2, but I need to put a negative. Okay, that gives me that my change in momentum, or my area under the curve, is 0.009. But that is not what I'm asking for. I'm asking for velocity after, so let's use the relationship that change in momentum is also mass times change in velocity. So 0.009 equals my mass, 0.001 change in velocity, divide over, get that my velocity changes by 9. Now when my velocity changes by 9, that means it's gaining 9 meters per second. So if it was -8 and it gains 9, then you're left with +1. Or if you don't like to think like that, you can use your change. The definition of change is final minus initial. So if your change was 9, I'm looking for V final, and my initial was -8, so subtract -8 becomes +8. Subtract that over, you get +1. Number 3, the following blocks of mass m and 3m collide and stick together. How much mechanical energy is transformed into internal energy? So we're going to draw our after picture. It's going to end up going to the right because you have more momentum to the right. I want to know how much energy is transformed. You can think about that mechanical energy. Mechanical energy is defined as like either kinetic or potential. In this case, you can assume this is on like a flat surface, so you're asking how much kinetic energy goes into other. So basically, how much kinetic energy is lost. This is an inelastic collision, so I know kinetic energy is lost, and it's asking how much is lost. Well, you can find the kinetic energy before pretty easily. Kinetic energy before is 1/2 3mv squared plus 1/2 mv squared. Direction doesn't matter for velocity. Even if it did, -v squared becomes +v. So then that is 3/2 plus 1/2. And if you don't have to like do the like finding, well, I guess it's already a common denominator, but you don't have to do it. You can just do like 3/2 plus 1/2 in your calculator and you get 2. So that's 2 mv squared. So I'm going to call this KE initial. My initial velocity started with was 2 mv squared. Now to find kinetic energy after, I would need to first know the velocity after. So let's use momentum. So 3 mv plus negative mv, because if it's going to the left, put a negative sign, equals, afterwards it's 3m. I'm not going to call it v because v has already been taken, so let's call it like x plus mx. So that's 4mx. The total momentum here is 2mv. M's cancel out, divide the 4 over, so in your x, your velocity after, is just 1/2 v. Okay, and now I can find my kinetic energy after. So my kinetic energy after, I'm going to think about it as like one block of 4m with a velocity of 1/2 v squared. 1/2 4m, when you square this, it becomes 1/4 v squared. The 4 and the 1/4 cancel each other out, so your kinetic energy after is just 1/2 mv squared. If it was 2 mv squared and now it's 1/2 mv squared, to find how much is lost, you just subtract. So 2 mv squared minus 1/2 mv squared. Well, like terms, 2 minus 1/2 is just 1.5. To put it in fraction form, math, enter, enter, that gives me 3/2. So I lost 3/2 mv squared. Equals 3/2 mv squared. So kind of a lot of work for that, because you had to find kinetic energy before, use momentum to find velocity after, find kinetic energy after, and then subtract to see how much was lost or transformed into other energies. Number 4, the graph to the left shows the position of the center of mass of a system at x as a function of time. The system is made up of multiple objects with a total mass of 2, and at time equals 2, there is an external force on the system. So we know there must be an external force because the center of mass should be continuing at the same velocity. This is a position versus time graph. So position versus time graph, to get the velocity from a position versus time graph, that's just the slope. So think about 1 meter in 1 second, another meter in 1 second. This one has a velocity of 1 meter per second. Then what happens is at this point there was some external force and now it's going faster. Now you look, in 1 second it goes up 3. Remember, velocity is just change in x over time, so you can just plug in like, oh, I did 2 meters in 2 seconds. Or in this case, from 2 to 5 is 3 meters in 1 second, so you get 3 meters per second here. That's a 3. So it goes from 1 meter per second to 3 meters per second. So obviously it's gaining velocity, which means it's gaining momentum. Change in momentum is just m. Change in velocity, your mass is 2. Velocity is v final minus v initial. This is my final, this is my initial, because I started this and then I went to this. So 3 minus 1. Or you can think about if you go from 1 to 3, you change by 2. Doesn't matter. Mass times change in velocity, would give me a change in momentum of 4 kilograms. So it gains 4 kilogram meter per second from here to here. Another position of center of mass is a function of time. Again, I have an external force because here I have a positive velocity and now I'm going backwards much faster. So obviously there was some external force to change my center of mass to velocity, given my mass. And to find change in momentum, m delta v. Now you could be like, wait, but I thought we were supposed to do area under the curve. Yeah, if we're talking about f delta t, and we're not looking at a force and time graph, so we're looking at position time. So we're going to use same relationships, but now to get velocity, you just look at the slope of the position graph. So here, again, it's going 1 meter per second. In 1 second, I go up 1 meter. So velocity is 1 meter per second. Call that v initial. And then here, first of all, it's negative, and it's going in 1 second, it goes down 3. So this one has a velocity of negative 3 meters per second. Now we plug in, mass is 0.5, change in velocity, negative 3 minus 1. Careful with your negative sign here, because if this was positive 3 versus negative 3, that's a much different change. So final minus initial, negative 3 minus 1 gives me negative 4 is my change in velocity, so then the change in momentum is negative 2. And the negative just meaning it's like losing, it's going in the negative direction now because it lost momentum, or it felt like an impulse in the negative direction. 6, a kid is riding in the wagon at the velocity of v, throws a, this is the kid, throws a ball out front with the velocity of 2v. And we were wondering, obviously the wagon's probably still going the same direction, but it would be slower because it gave some of its momentum away. We're wondering what the velocity of the center of mass of the two object system is now. Well, no external forces, it's the same as before, v. Number 7, blocks M and 3M move towards each other at the speed of v each. They two collide head-on and stick together. Which of the following best shows the momentum p as of the 3M block, both before and after? It says take right as positive, so that means this one is negative. So I know I start negative. When these two hit together, then there's more momentum to the left, so it's going to be going to the left still, but it's going to be slower because now this one, think about this one, has turned around, right? It was going to the right, now it's turned around. That's because it gave this one gave up some of its momentum to turn this one around. So now overall they are slower.